Welcome, curious minds, to another deep dive.
Great to be here.
Today, we're unpacking a fundamental yet often overlooked shift in how we think about sustainable construction.
Hmm,
For years, maybe decades even, when we talked about green buildings, the conversation was really dominated by operational energy.
absolutely. Things like efficient HVAC systems, better insulation, solar panels.
Right, all focused on how much power a building uses once it's up and running.
Yeah, keeping the lights on, the heat and going.
But as our sources are revealing, the focus is rapidly expanding. It's shifting to a much bigger, arguably more immediate problem.
Indeed. We're talking about the really significant impact of a building's upfront carbon cost.
Upfront carbon cost. Okay.
Yeah, it's the total carbon footprint embedded in its materials and the construction process itself.
Right.
To put it into perspective, think about this. For a new building, this embodied carbon can account for nearly half of its total lifetime emissions.
Half. Wow.
Yes, half. And all of that is released before the doors even open.
Before day one.
Before day one. So that's a massive initial investment in carbon, you could say.
Mm.
And that's really what we're diving into today.
It sounds like the next frontier, really, for sustainable design and construction.
I think that's exactly right. It has to be.
Okay, let's unpack this then. We've got a fascinating stack of sources for this deep dive. We're looking at everything from classic architectural histories, foundational project management guides,
And modern sustainability handbooks, too. A real mix.
a real mix. So our mission, as always, is to extract the most important nuggets of knowledge to help you understand this critical issue. We want to look at the powerful tools available to actually measure it.
Because measurement is key.
Definitely. And the innovative strategies emerging to tackle it head on. It's about building not just efficiently over the long haul, over decades,
Yeah.
but making sure we're building with the right materials and the right mindset from the very start.
From the first shovel in the ground. That's the idea.
Exactly. Okay, so section one, the shifting landscape. Let's talk about moving beyond just operational energy. For a long time, like we said, the image of a green building was pretty clear in our collective consciousness. Maybe a sleek building, solar panels on the roof.
Smart thermostats, really efficient windows.
Yeah.
That sort of thing.
Yeah. We focused intensely on reducing the energy consumed during a building's operational, life heating, cooling, lighting, plugging in all our stuff.
And let's be clear, that work is incredibly important.
Yeah.
It still is.
Absolutely vital. Our sources, especially one kind of sustainable construction, really drive home the scale of that challenge. They confirm that building energy consumption in the United States is roughly on par with transportation.
Which is huge.
It's huge, each consuming about 40% of primary energy.
40%. So nearly half our national energy pie just keeping buildings running and getting around. Operational efficiencies are absolutely non-negotiable. We have to keep pushing there.
No question. But what's truly fascinating now is how the conversation is evolving, right?
Yeah.
It's moving beyond solely the operational aspects.
Which, while crucial, only tell half the story. It's like reading the last chapter of a book first.
Yeah, good analogy. While operational efficiency remains vital, there's this growing, almost urgent recognition of the profound environmental impact of the initial building process itself.
Right. That sustainable construction source, for instance, explicitly notes that strategies for carbon footprint reduction are covered in Chapter 12.
Ah, so it's getting its own dedicated focus.
Exactly. It highlights that this upfront impact is now considered a distinct and critical area within the broader sustainability dialogue. This evolution acknowledges that a building's environmental story doesn't just begin when someone moves in.
It starts much, much earlier.
At its very conception, its design, the materials chosen, the construction.
And that source also connects the dots further, doesn't it? Linking the extraction and use of energy resources to wider consequences.
It does. It talks about the environmental impacts of extracting and consuming non-renewable energy resources, leading directly to things like, well, obviously climate change, but also land impacts from coal and uranium mining, acid rain, nitrous oxides, particulates,
The list goes on. Radiation, ash disposal problem.
long-term storage of nuclear waste. It's
Th-
not just a list. It gives you this broad, systems-level view of the full environmental cost.
It really paints a picture. It shows that our choices, the materials we pick, have these far-reaching effects way beyond the building site itself.
Long before we even plug in the first laptop in a new office, It impacts ecosystems, human health, globally.
So, okay, if operational energy is only part of the story, this upfront carbon cost, It sounds like a whole different beast.
It is.
From what the sources hint at, what exactly does that encompass? Where does this footprint really begin and end?
Well, you've pretty much hit on the core of it. The upfront carbon cost, or embodied carbon as it's often called.
Right, embodied carbon.
It's essentially the total greenhouse gas emissions associated with the materials and the construction processes of a building right up to its practical completion. Point zero, basically.
So before anyone moves in, the carbon debt incurred beforehand.
Exactly. Think about it.
Yeah.
It's the energy used to mine limestone for cement,
Okay.
to smelt iron ore to make steel,
Right.
to cut down trees and transport timber, to manufacture insulation panels.
And then all the energy used on the actual construction site.
Yep, the excavators digging the foundations, the cranes lifting beams, the trucks delivering materials, all of it.
It's a massive initial investment in carbon.
It really is. So for you, the listener, the learner, looking for that shortcut to being well-informed,
Yeah.
understanding this shift means grasping that sustainability in buildings starts long, long before the lights are turned on.
It starts with the dirt we dig.
The quarries we mine, the forests we harvest, the complex, often hidden industrial processes that turn these raw resources into the stuff of buildings, beams, concrete, glass, insulation.
It's like an invisible ledger of emissions attached to every single component.
Exactly.
Yeah.
Every step in that intricate global supply chain.
Yeah.
And this is why it's being called the next frontier. Because think about it, as our electricity grids get greener using more renewables.
Right. The operational carbon potentially goes down over time.
Precisely. Which makes this initial footprint, the embodied carbon, an even larger proportion of a building's total lifetime impact. It becomes more and more significant.
That makes sense. The upfront hit becomes harder to ignore.
Okay, section 2. This is where it gets really interesting, and it may be a bit daunting too. Material contributions to this upfront footprint, the implicit carbon hotspots. If we're talking about the carbon footprint of materials, where do we even begin to look? Our sources dive into the properties and uses of common building materials.
Yeah, lots of detail there.
But they also give us enough clues, I think, to infer where the biggest carbon culprits might be hiding. Like you said, the hidden costs. Yeah, if we connect the dots, looking at the bigger picture of emissions, we can definitely infer these carbon hotspots. We look for materials that need significant processing or just have inherent energy intensity baked into their production.
And sources like structures or why things don't fall down or even that old mining treatise to Ray Metallica.
Right. They provide both contemporary and historical context. They help us understand the immense effort and therefore the energy and carbon involved in bringing these materials to life.
It's a journey from raw earth to finished product.
And every step adds to that upfront carbon cost, often in ways we just don't immediately see.
Okay, let's start with the big one. Concrete.
The foundation, literally.
It is absolutely everywhere. It's the bedrock of so much of our modern world. Foundations, columns, bridges.
Sidewalks, dams.
It's strong, it's durable, relatively inexpensive. But are all concretes created equal when it comes to their environmental impact?
That's a crucial point. And it's where the nuances of embodied carbon really start to matter.
Because we use different types for different jobs, right?
Exactly. Fundamentals of Residential Construction details that there are actually 8 different types of Portland cement.
8 types. Wow. Okay.
And Portland cement is the key binding ingredient in concrete, the glue that holds it together. These range from Type I normal, which is your standard general-purpose cement,
Right.
to things like Type V high resistance to sulfate attack, used in specific harsh environments where durability against chemical attack is paramount.
Okay, but where does the carbon insight come in?
Well, think about Type 3 high really strength cement. It's incredibly useful for accelerating construction schedules, maybe pouring concrete in cold weather when you need it to set faster.
Saves time, saves money, perhaps.
Potentially. But producing Type 3 often requires more intensive grinding of the clinker, the raw material, and potentially higher kiln temperatures during its production.
So more energy input.
More energy input, which means a potentially higher upfront carbon cost for the convenience of faster curing.
Interesting trade-off.
It is. Conversely, you have Type 4 low heat of hydration. This is designed for massive structures like dams.
Why low heat?
Because when huge volumes of concrete cure, they generate a lot of heat. If that heat builds up too quickly in a massive pour, it can cause thermal stresses and cracking.
Okay, makes sense.
So Type 4 slows that down. And this might allow for greater material efficiency in these vast pours, maybe reducing the total volume of cement needed for such enormous projects.
So the subtle shift in the cement type itself can carry a significant carbon price tag or maybe an opportunity for reduction.
Exactly. That's the key insight for you, the discerning listener. It's not just concrete, it's which concrete and why. And that leads to another really crucial lever for reducing concrete's footprint:
Okay.
admixtures. The same source, Fundamentals of Residential Construction, mentions blast furnace slag.
Slag, what's that?
It's a byproduct of iron manufacture. Basically, it's waste material from making iron and steel. And it can be used as a concrete admixture, partially replacing some of the Portland cement.
So using waste from one industry as a resource in another.
Precisely. It immediately raises a critical question for you. Could modifying concrete mixes with these industrial byproducts, slag, or maybe fly ash from coal power plants, be a powerful way to significantly reduce concrete's carbon footprint?
That sounds like a huge opportunity. Circular economy thinking right there.
As a prime example, waste becomes a valuable resource, cutting down the need for virgin cement production, which is the most carbon-intensive part.
And it's not just the mix, right? Design choices matter too.
Oh, absolutely. Building Construction Illustrated highlights the precision needed in concrete engineering. It gives a rule of thumb for estimating depth of a concrete beam, span 16.
Okay, a design guideline.
And it advises designers to vary required steel reinforcement rather than beam size.
Why does that matter for upfront carbon?
Because every extra pound of steel reinforcement, every unnecessary cubic foot of concrete in that beam, carries an embodied carbon burden.
Right, the materials themselves have a footprint.
So this precision in design isn't just about structural integrity or cost. It's a powerful tool to right-size our material use, to use only what's truly needed.
We don't just want strong. We want just strong enough.
Exactly. That efficiency directly cuts down on emissions. And it's not a new idea, really. Even ancient practices show this kind of thinking.
How so?
The 4 books of architecture, Palladio's work, describes how foundations on soft ground often needed piles.
Okay, deep foundations.
And he gives specific proportions. Their length ought to be the 1/8 part of the height of the walls, and their thickness the 12th part of their length.
So precise calculations even then.
It demonstrates this long history of tailoring material use very carefully to specific site conditions and structural needs. That principle, using materials wisely, is just as vital today for minimizing carbon consumption. Maybe even more so.
Okay, let's move on to steel and metals. The backbone, the skeleton of so many modern structures.
Especially tall buildings, long bridges.
Metals, particularly steel, are foundational. Strength, versatility. But how do they compare in terms of that weight cost idea, and what does that imply about their broader environmental costs, their embodied carbon?
Well, structures, or why things don't fall down, provides a really striking insight here. It says that steel comes out rather badly, even compared with bricks and concrete, when you consider the weight cost of carrying a compressive load in a column.
So pound for pound, it's more resource intensive for that specific job.
Essentially, yes. For that particular structural function, carrying compression, it implies a higher resource, and energy intensity is needed to get the job done compared to concrete or brick, purely on a weight basis.
That immediately flags steel as a significant potential hotspot for embodied carbon then.
It does. Its strength is undeniable, particularly in tension, which is why it's used in beams and bridges. But it comes with a carbon cost that goes way beyond the dollar amount.
And history shows we've used a lot of it.
Oh, absolutely. Sources like A History of Architecture Settings and Rituals and The Pattern of English Building remind us of this long-standing, widespread reliance on iron and steel.
We're talking structures going way back.
Yeah, think of the pioneering iron bridge from 1777-81. That was the first time in an important structural capacity for cast iron on that scale.
Wow.
Or the massive cast iron ribs of the Sunderland Bridge a bit later, or the wrought iron chains holding up Telford's Menai Strait Bridge.
These examples really illustrate the sheer scale of metal usage that defines centuries of industrialization and construction.
They do, and they underscore its cumulative environmental impact over time. Each one represented a huge investment in mining, smelting, transport.
Which brings us to that really old source, Durae Metallica.
Yes, from the 16th century. It's perhaps the most illustrative source for understanding the deep embodied energy in metals.
Because it describes the process itself.
Vividly, it details the intricate, often grueling processes involved back then in obtaining metals like gold, silver, copper, and tinstone.
What kind of processes?
Everything from extensive sieving and washing of the raw ore, which required significant water and manual labor, to the continuous, intense melting of slags, the impurities that are drawn off during purification in furnaces.
It sounds incredibly labor and energy intensive even then.
It was. This extensive background provides a stark picture of the industrial and energy-demanding nature of metal extraction and processing going back centuries.
So the key takeaway for you, listening in, whether you're a pro or just an observer,
Is how incredibly energy-intensive these processes have always been, fundamentally. This complex, multi-stage journey from ore in the ground to a finished beam.
it directly translates into a substantial environmental footprint, long before that beam ever arrives on a construction site.
Exactly. It's a powerful reminder that these materials don't just appear. They are wrested from the earth and refined through demanding high-energy processes. That makes their embodied carbon footprint a really significant challenge to address.
Okay, let's shift gears. Wood and mass timber.
The renewable option.
Often touted as such, yes. Wood is a naturally renewable resource. It sequesters carbon dioxide as it grows, and in theory, we can replant forests.
On the surface, it sounds like a great solution compared to concrete and steel.
It does. But what do our sources tell us about its modern applications? Especially this thing called mass timber. And are there nuances we should consider regarding its true carbon footprint? Is it always the greener choice?
Well, the perception of wood as renewable and generally lower carbon holds true in many cases. But like everything in embodied carbon, it's not quite that simple. There are complexities.
Okay.
Building Codes Illustrated, for example, reveals how modern timber is being engineered for entirely new applications. We're moving way beyond just traditional 2x4s.
Right, this mass timber. What is that exactly?
It's a sophisticated engineered product. Think of large structural panels, posts, and beams made by laminating layers of wood together under pressure with adhesives. Things like cross-laminated timber, CLT, or glulam beams.
So engineered for strength, allowing wood to be used in bigger buildings.
Precisely. The codes even have new classifications, like Type IV mass timber construction, and they get specific about fire safety. For instance, mass timber elements in buildings of Type IVA construction must be fully protected with things like drywall,
Okay.
while isolated mass timber columns may be unprotected in Type IVB construction in certain situations. There's also a need for specific fire resistance ratings for connections in these types of construction.
So a lot of engineering and safety considerations go into using it in larger structures.
Definitely. These details show that mass timber isn't just a simple block of wood. It's a precisely manufactured component, and that manufacturing the laminating, the adhesives, the energy used in the pressing, plus the transportation and careful installation, that all contributes to its embodied carbon.
It's not zero carbon just because it's wood.
Not at all.
Yeah.
And even beyond these advanced applications, think about traditional wood light framing, the kind used in most houses. Fundamentals of Residential Construction talks about optimizing rafter stands. Like a 2x6 can span up to 10 feet, a 2x12 can span up to 22 feet.
So choosing the right size for the job.
Exactly. Again, it shows how design choices directly affect the quantity of material needed, even for a simple wood frame. Making smarter choices about sizing, optimizing structural elements,
Yeah.
that's a direct way to reduce material demand and, consequently, embodied carbon. Use less wood, even if it's renewable.
And the wood itself needs processing, right? It doesn't just come perfectly ready from the tree.
Good point. Understanding wood reminds us that even this seemingly natural material requires significant processing to be fit for construction.
Like what?
It delves into the biology distinguishing ring-porous woods like oak from diffuse-porous woods like maple. But critically, it details the process of drying wood, kiln drying usually,
Why is drying so important?
to control shrinkage and ensure stability. Wood shrinks and can warp as it loses moisture, so drying involves careful control of shrinkage-related stresses.
And that drying process takes energy.
It does. Kilns require heat, often generated by burning natural gas or biomass,
Right.
so that adds to wood's own embodied carbon footprint.
So the key insight here is that even the most natural materials have an industrial journey.
Right. And understanding that journey from sustainable harvesting, hopefully, through processing and transport, is vital for a true embodied carbon assessment. It's usually better than steel or concrete, but it's not zero.
Okay, one more major category. Building enclosure and insulation. The building skin.
The thermal envelope. This is
The
critical
critical.
because these materials play a dual role. They have their own significant upfront carbon impact from their production and installation.
Okay, they're embodied carbon.
Right, and then they continue to influence operational energy throughout the building's entire life by keeping it warm in winter and cool in summer.
Ah, so this is where embodied carbon and operational carbon directly interact.
Exactly. This intersection in the building envelope is a really critical area of focus for sustainable design.
That's a fascinating point about the dual role. It means the choices we make for the enclosure, from the siding or brick on the outside to the hidden insulation layers inside the walls, they determine not only how much energy the building will consume day to day,
Your heating and cooling bills.
but also the upfront embodied carbon we're investing right at the start. It sounds like a complex balancing act.
It absolutely is.
Because a material that's great for reducing operational energy might have a really high embodied carbon cost to produce.
That's the potential trade-off you constantly have to evaluate. And our sources shed light on this. Builder's Guide to Hot, Dry, and Mixed Dry Climates, for instance, highlights the increasing sophistication in managing thermal performance.
How so?
It discusses things like vapor retarders, cavity insulation, the fluffy stuff between studs and rigid insulation boards, often used on the exterior.
All crucial for energy efficiency.
Crucial, but all these layers, all these different materials have their own production footprints, their own embodied carbon stories.
Can you give an example of that trade-off?
Sure. Consider insulating concrete forms, or ICFs. Fundamentals of Residential Construction mentions these.
ICFs. What are they?
They're basically hollow blocks made of polystyrene foam, like Lego blocks. You stack them up to form walls, reinforce them with steel rebar, and then fill the hollow cores with concrete.
And the foam stays in place.
Yes, the foam forms are left in place to add thermal insulation to a concrete wall. They create strong, well-insulated walls and are rapidly gaining popularity.
So great for thermal performance, reducing operational carbon.
Definitely. It's a material choice explicitly designed to drastically improve thermal performance. But
the foam itself.
exactly.
Right.
We have to acknowledge that the polystyrene foam, derived from fossil fuels and its manufacturing process, has its own embodied carbon cost. That needs to be weighed carefully against the long-term operational savings.
A classic embodied versus operational calculation.
It really is. And building codes also play a role here. Building Codes Illustrated outlines regulations, like requiring a thermal barrier, maybe half-inch gypsum wallboard or even heavy timber, to separate foam plastic insulation from the building interior for fire safety.
Ah, so another layer of material needed.
Another layer, potentially adding to the complexity and the overall embodied carbon tally. Every component matters.
It sounds incredibly detailed.
It is. And Fundamentals of Building Construction gives this fascinating detail about designing exterior walls, windows, and doors to neutralize 5 forces that can move water through an opening.
5 forces, like what?
Gravity, momentum, wind-driven rain, surface tension, capillary action, water wicking into small cracks, and air pressure differences.
Wow, okay, that's complex.
It underscores the immense complexity of the building envelope. Every component, every joint, every flashing, every seal, it all has an embodied impact from its manufacturing and installation. Achieving both superior operational efficiency and low embodied carbon footprint in the envelope. That requires a truly holistic approach.
You have to look beyond just the R value of the insulation.
Way beyond. You need to consider the entire life cycle impact of every single piece of that building skin.
Okay, section 3. Tools and best practices. This feels crucial. With so many materials, so many processes, from mining ore to drying timber, all these nuances about concrete types and foam insulation, how do we actually measure this upfront carbon cost?
Yeah, it sounds incredibly complex, right? Almost impossible to track everything.
It does. But our sources point to a couple of key approaches that are bringing much-needed rigor to this challenge, moving beyond guesswork.
You're right, it sounds daunting, but we have to ask, how do we shift from just having an anecdotal understanding, these inferred hotspots, to getting quantifiable, auditable assessments?
Numbers we can actually use.
The answer lies in systematic analysis. And fortunately, the industry is developing some powerful tools to do just that. We're moving from intuition to data-driven decisions. And one of the most critical tools in this shift is life cycle assessment, LCA.
LCA. Okay, what is that?
The Sustainable Construction Source introduces a specific example, BEES 3.0. It's described as a free LCA program available from the National Institute of Standards and Technology, or NIST.
Free. That's good.
It is. And it's a crucial, accessible tool. It allows for quantitative analysis of the environmental impacts of building materials and products throughout their entire life cycle.
Entire life cycle. So cradle to grave.
Pretty much. From raw material extraction through manufacturing, transportation, installation, use, maintenance, and then finally end-of-life disposal or recycling.
That level of detail moves us way beyond just simple assumptions about whether a material is green.
It gives us hard data, numbers we can compare.
Okay, so LCA is the method. What about the results?
That's where environmental product declarations, or EPDs, come in.
EPDs, right.
The source clarifies their role. These are standardized, third-party verified reports. Think of them like nutrition labels, but for environmental performance.
Okay, I like that analogy.
They transparently communicate the environmental performance of a specific product, including its embodied carbon, based on LCA data. Sustainable Construction states they are now important in the arena of selecting high-performance building materials and products.
So designers can use these to pick lower impact options.
That's the goal. However, there's a catch. The source wisely notes that EPDs are not especially helpful in isolation.
Why not?
Because to be truly effective, you need a significant number of EPDs available in each product class. For example, you need EPDs from multiple manufacturers of, say, ceiling tiles or carpet or insulation to allow comparison among like products.
Right. If only one company provides an EPE, you can't really compare it to anything.
Exactly. We need broad transparency across the market for meaningful selection. We need manufacturers to step up.
So the ultimate goal isn't just product-level EPDs.
No, the ultimate goal, as the source puts it, is whole building comparisons that combine EPDs into an EBO, which stands for Environmental Building Optimization.
Okay, EBO.
This would allow trade-offs between systems. It indicates this desire for integrated, comprehensive assessment.
So you could see if using a slightly higher carbon floor system allows for a much lower carbon wall system and evaluate the net effect.
Precisely. It's about understanding the ripple effect of every choice, not just in isolation, but as part of the larger building system, optimizing the whole building's carbon footprint.
Okay, so LCAs give us the methodology, EPDs give us the product data, but what about integrating all this not just for materials, but for the entire design and construction process itself? How can we make informed decisions really early on, basically building the whole thing virtually before we even break ground?
This is where digital tools, specifically building information modeling, or BIM, come into play. And they are truly offering a revolutionary approach.
BIM. Heard a lot about it. More than just 3D models.
Oh, much more. The BIM handbook rightly calls object-based parametric modeling the core of BIM, revolutionary in their impact. It notes BIM can play an important role for design, analysis, checking, display, and reporting.
So it's intelligent modeling.
It is. CMAA Construction Management Standards of Practice elaborates on BIM's power, calling it a superior design environment when compared to traditional 2D CAD.
Why superior?
Because of its ability to capture design intent parametrically. That means objects in the model know what they are and how they relate to each other. If you change a wall's length, the associated floor area, material quantities, maybe even cost, can update automatically.
Wow.
This facilitates model creation and editing, and therefore reduces the likelihood of coordination errors. Imagine designing a wall, and the software automatically knows its material, its insulation value, its fire rating, maybe even its embodied carbon, based on linked EPD data.
That's powerful.
It is. At its core, BIM contains a digital database. It's a virtual representation of a physical facility where objects, spaces, and facility characteristics are defined and stored.
And this virtual model lets you do analysis.
Exactly. Various kinds. Structural, energy consumption, daylight analysis. But what's particularly impactful for reducing embodied carbon during construction is BIM's ability to do clash detection.
Clash detection. Finding conflicts.
Yep. It's a process to check for interferences by searching for intersecting volumes in the digital model.
Like where a pipe might run straight into a steel beam.
Precisely. Or where ductwork might conflict with electrical conduit. BIM highlights these clashes before they happen on site.
That must save a lot of hassle.
And waste. This can greatly reduce coordination errors between systems during construction, preventing costly rework, material waste, delays, all of which directly contribute to embodied carbon. It's catching mistakes before they ever leave the computer screen.
That real-time clash detection sounds like a game changer for efficiency and waste reduction, which obviously has direct carbon benefits. But BIM goes even further, right? It integrates time and cost.
Absolutely. It offers this profound integration. For project management, you have 4D BIM.
4D, time being the fourth dimension.
You got it. A 4D BIM scheduling application can dynamically link the project CPM schedule activities, that's the critical path method schedule, to 3D objects in the BIM model.
What does that let you do?
It allows for a graphically rich and animated representation of the planned construction sequence set against time. You can literally watch a virtual construction of your building unfold day by day or week by week.
So you can spot potential bottlenecks or inefficiencies.
Exactly. In material delivery, crew sequencing, equipment use, this visualization helps optimize the construction plan, potentially reducing equipment idle time, transportation impacts, site waste. It all helps lower the embodied carbon of the construction phase itself.
And then there's 5D.
Yes, 5D adds cost management. 5D cost management capabilities allow every element in a BIM model can be attributed to what it will actually represent in terms of resources and respective costs.
So automatic cost estimation linked to the model.
And more than that, a parametric and dynamic quantity takeoff for bills of materials. You get precise material lists and costs instantly as the design evolves.
Which means less waste from over-ordering.
Precisely. This level of detail allows for accurate material estimation, minimizing waste, and it enables designers to evaluate the costs, both financial and environmental, if carbon data is linked to different material options with unprecedented accuracy very early in the design process.
Project management in construction reinforces this too, right? Highlighting the shift from 2D drawings.
It does. It stresses how moving from 2D construction drawings to 3D and 4D computer-assisted design is crucial, especially to anticipate those interference problems, like needing to reroute piping or ductwork on site that would otherwise lead to changes, waste, and delays.
So it's not just about what the building looks like, but its entire planned life cycle, digitally modeled and optimized. There's a source, the City of Tomorrow, that offers this really compelling vision for this deep integration.
Yeah, that's a fascinating perspective. It describes how the very process of creating architecture could become an iterative chain rather than a directly linear process.
Iterative, not linear. Meaning
the distinct phases we usually think of, design, documentation, construction, and inhabitation, don't just happen one after the other in isolation.
No.
As each step transitions to digital systems, the whole process will be unified.
so they talk to each other.
Exactly. This integration enables phases to inform one another, structuring a codependent feedback system, and ultimately, a full merger.
A full merger. That sounds like a fundamental paradigm shift.
It really is. What's profound about this vision is it moves beyond just digitizing the old workflows. It proposes a fundamental restructuring of the entire architectural production chain.
Oh, so?
By creating this continuous feedback loop, decisions made in the very early design stages can be immediately evaluated for their impact on constructability, on cost, and crucially for our discussion, on embodied carbon.
So you can optimize constantly.
Right. Optimization at every step becomes possible. It makes achieving much lower carbon footprints feasible because you're addressing issues before they become fixed in physical form. You're preventing problems rather than just reacting to them later.
So for you listening, these digital tools, BIM, LCA, EPDs, they aren't just technical jargon.
Not at all. They represent a fundamental shift in how buildings are conceived, designed, and constructed. They offer unprecedented opportunities to understand and manage their carbon impact from the earliest possible stages.
They're essential enablers for this next frontier of sustainable design.
Absolutely, allowing us to build smarter, leaner, and with far greater foresight about the true environmental cost.
Okay, Section 4, emerging policies and rating systems driving the change.
Mm-hmm.
So we know there's this big problem with upfront carbon. We're developing these sophisticated tools like LCA and BIM to measure and model it. But what about the bigger picture? How are industry standards, maybe even government policies, starting to move the needle? How do we push these considerations into mainstream practice beyond just the passionate early adopters?
Yeah, that's the critical question of scale, isn't it?
Yeah.
If we connect this to the bigger picture, it's clear that top-down guidance, or at least structured frameworks, are absolutely crucial to institutionalize these changes.
So individual efforts are great, but we need systemic drivers.
Exactly. Policies and rating systems are emerging as powerful drivers. They set the benchmarks, the requirements, sometimes offer incentives that transform industry practice. They provide both the carrot and the stick for change. One significant initiative that really sets a clear, ambitious target is the 2030 Challenge.
The 2030 challenge. Heard of that. What's the goal?
Fundamentals of Residential Construction describes it as a voluntary program for architects. It sets this bold goal, committing design professionals to develop practices that will produce carbon-neutral buildings by the year 2030.
Carbon neutral by 2030. That's ambitious.
Extremely ambitious. It signals a clear target for the entire design industry. And the program explicitly acknowledges the scale, noting that buildings consume 49% of total national energy use and produce 47% of carbon emissions.
So it underscores the urgency. Does it focus only on operational carbon?
Well, its primary focus initially was heavily on operational carbon reduction, energy efficiency, and renewables. But the very nature of striving for total carbon neutrality by such a firm deadline,
It forces you to look at embodied carbon, too.
it inevitably brings embodied carbon into sharp focus. You simply cannot reach net zero carbon overall if you ignore half the problem, that massive upfront footprint. So it implicitly and increasingly explicitly pushes towards addressing embodied carbon as well.
Now, long before many people were even talking about embodied carbon specifically, LAD was a huge force in green building.
Oh, absolutely. OLED, or Leadership in Energy and Environmental Design.
It really brought environmental considerations to the forefront for countless projects, became almost a household name.
Exactly. Fundamentals of Residential Construction identifies the U.S. Green Building Council, USGBC, and their LEED program as a notable agency promoting green projects.
Yeah.
It offers several levels of certification, silver, gold, platinum,
Right.
under 5 different categories covering various aspects of sustainability.
And while it was traditionally very strong on operational energy,
And other things like water use, site selection, indoor environmental quality.
it set this powerful precedent for structured environmental assessment.
It really did. It played a massive role in raising awareness and driving change across the industry. Its comprehensive point system, even if not initially heavily weighted on embodied carbon specifically.
It got people thinking in those terms.
It accustomed the industry to thinking in measurable environmental terms, documenting choices, and proactively seeking sustainable solutions. In many ways, LED laid the essential groundwork for the deeper, more focused embodied carbon discussions we're having today. It created the framework and the expectation.
Okay, so LED was foundational, but then you have systems that push the boundaries even further. This raises an important question. What happens when you set the bar incredibly high? When you demand not just better, but truly regenerative outcomes?
That's where the Living Building Challenge, or LBC, comes in. It really pushes the envelope, almost daring architects and builders to rethink everything.
How is it different from LEED?
Well, sustainable construction describes the LBC as the clear leader in building assessment systems in terms of degree of difficulty.
The clear leader in difficulty. Okay.
Unlike LEED's point system, which allows flexibility, you pick and choose credits to reach a certain threshold, the LBC operates on a much more stringent principle. It has 20 prerequisites.
Prerequisites, not optional credits.
Exactly. They are only mandatory requirements. A building either is certified to LBC or is ineligible. There are no shortcuts, no partial credit. It's all or nothing.
Wow. What kind of demands does it make?
Extremely stringent ones. It requires achieving net zero energy, NZE, meaning the building produces on-site as much renewable energy as it consumes annually.
Okay. Net zero energy.
And net zero water, meaning it captures and treats all its water on-site. No municipal water or sewer connections.
Net zero water, too. That's tough.
Very tough. It also has to be non-toxic in its materials, avoiding a whole red list of harmful chemicals. It has to provide for habitat restoration on sites, actively improving the ecosystem, and even incorporate urban agriculture.
It sounds incredibly holistic.
It is, but here's what's truly fascinating and really sets it apart as a true gold standard.
Yeah.
Certification can be achieved only after 1 year of operation that demonstrates the building has met its objectives.
So you have to prove it works, not just promise it will.
Exactly. It's not about design intent or simulations alone. It's about proven performance. This performance-based approach mandates actual, measured sustainability over a full year cycle.
That's a huge difference.
It is. The source gives a great example. The Tyson Living Learning Center. It initially produced more electricity than needed, but adjustments were still required to fine-tune systems to meet the precise NZE level consistently.
And they didn't just add more solar panels.
No, crucially, the team chose to add insulation, retrofit storm windows, and adjust the HVAC system first. They focused on reducing demand before just adding more generation. It shows this deep commitment to real, measured performance.
And how does this relate to embodied carbon?
Well, this level of rigor, spanning energy, water, materials, toxicity, ecosystem health, it naturally encompasses a deep consideration for embodied carbon. You simply can't achieve this level of holistic sustainability without being incredibly careful about material selection, minimizing waste, and reducing those upfront carbon costs from the very outset. It forces that conversation. And beyond these prominent examples, other robust systems are also driving change.
Like what?
Green globes, for instance. The source notes it represents more than 20 years of research and refinement. It actually originated from BREEAM, the Building Research Establishment Environmental Assessment Method in the UK.
BREEAM, right. One of the originals.
Exactly. One of the world's first and most influential green building rating systems. Green globes, drawing on that history, aims to accelerate the adoption of building practices that result in energy-efficient, healthier, and environmentally sustainable buildings.
So another pathway for projects.
Right. These diverse, yet often interconnected systems, LE, LBC, Green Globes 2030 Challenge, they provide different pathways, different levels of stringency. But they all contribute to this broader movement towards more responsible construction. And increasingly, they are all finding ways to explicitly address and incentivize reductions in embodied carbon.
So connecting the policy to the practice.
The trend is clear. These policies and rating systems are moving beyond just advocating for efficient buildings, focused only on operation.
They're demanding more.
They're increasingly demanding responsibility for that massive upfront carbon cost of new construction. They're actively pushing the industry to think about and act on building with the right materials from the start.
And this isn't just an abstract ideal. It affects day-to-day work.
Absolutely. It's becoming integrated into the practicalities of project management itself. That CMAA, Construction Management Standards of Practice source, even notes that when a project aims for sustainability, especially ELE certification, things like requests for additional information or needing credit interpretations become part of the workflow. Construction managers have to deal with documenting these environmental goals.
So it trickles down into the paperwork, the submittals, the daily grind.
Exactly. It shows how these environmental goals, driven by certification systems, impact everything from initial documentation and material sourcing decisions to contractor responsibilities and even budget allocation. This top-down guidance, these frameworks, are essential for making embodied carbon a primary design consideration.
It helps transform aspiration into actual requirements.
And literally changes how buildings get built from the ground up, or maybe from the EPDs out.
Okay, Section 5, an urgent call to action, responsibility from the start. So, after all this, what does it all mean for us? For you, listening, as we think about the future of our built environment, we've seen that this cost of carbon in construction, it's not just about the building's electricity bill.
Not just the solar panels on the roof.
Right. It's about every single material choice, every manufacturing process, every design decision made long, long before that building even opens its doors.
It's this massive front-loaded investment in carbon.
An investment we can no longer really afford to overlook.
Exactly. The sources, when you read them through this lens, they provide an urgent, I think, undeniable call to action.
From ancient wisdom to modern tech.
Right. From those ancient insights into material properties and structural optimization, think Palladio knowing exactly how thick to make his piles, to the vivid historical accounts of just how resource-intensive metal extraction has always been in Re Metallica, and right up to today's modern digital modeling with BIM and these rigorous certification systems like the Living Building Challenge. The industry is clearly gathering the knowledge and the tools needed.
We have what we need to take responsibility.
We do. To take responsibility for this massive upfront carbon investment. We have the data, we have the technology, we have the guiding principles to make profound changes. We're moving past just being aware.
Towards being accountable.
Yes, actively accountable.
It feels like it's about recognizing that the truly greenest building might actually be the one that minimizes its footprint from day one, its embodied carbon, not just the one that performs well over decades of operation. Though that's important too.
It has to be both, ultimately. But this shift in focus to embodied carbon means a more holistic and, frankly, a more honest accounting of our environmental impact.
Honest accounting. I like that. It's like realizing the biggest part of your home's environmental debt isn't the monthly utility bill,
but the enormous carbon down payment made during its construction.
And that you actually have more control over that down payment than maybe you previously thought.
Precisely. So for you listening, this deep dive really shows that being truly well-informed in sustainable design today means looking beyond the obvious,
Beyond the solar panel.
beyond the solar panels, understanding the invisible costs, the embodied carbon, and recognizing the power of informed decisions at every stage, starting right at the beginning.
It's about creating value, not just in the finished building,
Right.
but in the entire journey of its creation. This means challenging conventional wisdom sometimes, maybe questioning standard material choices,
Digging into the specifics of material science, using those EPDs.
leveraging those cutting-edge digital tools like BIM to make choices that are truly sustainable, reducing that initial carbon burden as much as possible,
It's about building for longevity and resilience, sure.
but also for minimal impact from the very beginning. That's the goal.
Wow, what an incredible journey through these uh, often hidden environmental costs of our built environment.
It really is fascinating when you start to peel back the layers.
From the ancient art of working with metals and stone, understanding their inherent properties, to the absolute cutting edge of BIM-driven design and those incredibly ambitious performance-based goals of the Living Building Challenge.
It's just abundantly clear that how we build is now just as important, maybe even more critical in the short term, as what we build.
It completely reframes the concept of a green building, doesn't it?
It really does.
And it reminds us that our structures aren't just static objects sitting there. They are complex systems. They have this profound, dynamic relationship with our planet.
Both in their long-term operation
And in their immediate creation.
Ah.
Every single material has a story, a history of extraction, transformation, transportation that carries an environmental price tag, an embodied carbon cost.
and recognizing that price tag, quantifying it with tools like LCA and EPDs, and then actively working to reduce it.
That truly is the next great frontier for sustainable design and construction. It's where the biggest challenges and maybe the biggest opportunities lie right now.
So here's a final provocative thought for you, our listeners, to mull over. If ancient builders, people working centuries ago, without our modern computational tools, without LCA databases or BIM, if they still made incredibly deliberate, sophisticated choices about materials and site, choices that led to structures like the Pantheon or the great cathedrals that have endured for centuries.
Often using local resources with incredible ingenuity.
Exactly. With this deep, intuitive, or maybe just hard-won understanding of their local resources and long-term performance. If they could do that then, what unique responsibility do we have today?
We, with our advanced data, our global supply chains, our powerful technology, our comprehensive understanding of life cycle impacts.
What's our responsibility to design and build for a future that is not just efficient in operation, but fundamentally regenerative from the ground up?
Regenerative, meaning giving back more than it takes.
Yeah. What if choosing the right materials from the start, the lowest embodied carbon options that still meet performance needs? What if that isn't just a smart design choice anymore?
What if it's more?
What if it's a moral imperative for every single project moving forward? A cornerstone of the legacy we leave behind in the built environment.